Welcome to an exploration of computational abduction, where machines learn to generate hypotheses like scientists do. Computational abduction represents a paradigm shift in how artificial intelligence reasons about data, moving from testing given hypotheses to generating new explanations. Let's start by understanding what abduction means in logic and reasoning. Abduction is a form of logical inference where we work backwards from observations to find the best explanation. Unlike deduction, which goes from rules to conclusions, or induction, which generalizes from examples, abduction generates hypotheses that could explain observations. Consider the classic wet grass problem that illustrates abductive reasoning. You observe that the grass outside is wet. Abduction generates possible explanations. It rained, the sprinkler ran, or dew formed overnight. Each hypothesis has different probability and explanatory power, and abduction helps us reason about which is most likely. How does abduction differ from deduction and induction? Deduction applies known rules to specific cases to derive certain results. Induction observes many cases and results to generalize a rule. Abduction takes known rules and observed results to hypothesize which case might have occurred. Here's a comparison of all three types of reasoning with concrete examples showing their logical structure. Let's formalize computational abduction mathematically. At the heart of computational abduction is Bayes' theorem, which calculates the probability of a hypothesis given evidence. P of h given E is the probability of our hypothesis being true given the evidence we observed. P of E given h is how likely we would see this evidence if our hypothesis were true. P of h is our prior belief about how likely this hypothesis is before seeing evidence. P of E is the overall probability of observing this evidence under all possible explanations. Here's a numerical example. If the likelihood is 0.9, prior is 0.3, and evidence probability is 0.4, then posterior probability is 0.675. How do we implement abductive reasoning in computers? First, we define the space of all possible hypotheses the system can consider. Second, we assign prior probabilities based on domain knowledge or uniform distribution. Third, for each hypothesis, we compute how well it explains the observed data. Fourth, we use Bayes' theorem to calculate updated probabilities given evidence. Finally, we rank hypotheses by posterior probability and select the most plausible ones. This diagram shows the computational pipeline. Input hypotheses flow through a Bayesian reasoning engine that outputs ranked probabilities. Let's see computational abduction applied to medical diagnosis. A patient presents with fever, cough, and fatigue. The question is, what disease or condition best explains this combination of symptoms? The system generates candidate diagnoses like flu, common cold, or COVID, each with different explanatory power. Computing posteriors. We might find flu has probability 0.45. Common cold has probability 0.35. And COVID has probability 0.20, given just these symptoms. Based on these probabilities, the system recommends testing for flu as the most likely diagnosis. Let's examine the core algorithm more closely. The scoring function multiplies the prior probability by the likelihood of each piece of evidence given the hypothesis. When we have multiple independent pieces of evidence, we multiply their individual likelihoods. The best hypothesis is the one that maximizes this score function. Evidence pieces flow into the scoring function, which outputs ranked hypotheses based on their explanatory power. Real-world abduction must handle uncertainty and incomplete information. One challenge is dealing with missing evidence, where we don't observe everything relevant. We handle this by marginalizing over unknown variables, integrating them out of our calculations. Mathematically, we sum over all possible values of unknown variables u. Another challenge is noisy observations, where measurements contain errors. We use probabilistic likelihood models that account for measurement noise and uncertainty. This visualization shows how observations form an uncertainty cloud around the true values we're trying to infer. The most powerful aspect is generating hypotheses not predefined by humans. Traditional AI systems can only test hypotheses from a fixed, pre-programmed set. Computational abduction can create entirely new hypothesis structures not imagined by designers. You might ask, how does the system know what hypotheses to generate? The answer is through compositional combination of primitive concepts following learned patterns. Primitive concepts A, B, and C are compositionally combined to generate novel compound hypotheses like AB, AC, and BC. Computational abduction mirrors how scientists make discoveries. Consider discovering chemical reaction mechanisms from experimental data. We input the reactants, products, and reaction conditions observed. The system outputs hypothetical intermediate steps and possible catalysts that could explain the transformation. From known reactant A and product B, the system hypothesizes intermediate species X and Y that could mediate the transformation. The probability of each mechanism given the data is proportional to how well it explains the data times its prior plausibility. This approach has been used successfully to elucidate complex enzyme catalysis pathways in biochemistry. Despite its power, computational abduction faces practical limitations. First, the hypothesis space can be exponentially large, making exhaustive search computationally intractable. The number of hypotheses often grows as k to the power n, where n is the problem complexity. Second, multiple incompatible hypotheses may equally well explain the same data. Third, there's a trade-off between generating creative novel hypotheses and ensuring they're scientifically sound. These three key challenges, computational cost, multiple valid explanations, and balancing novelty with validity, define the current frontiers of research. Let's look at how modern systems implement computational abduction. Probabilistic programming languages, like Church and Web PPL, provide frameworks for abductive inference. Neuro-symbolic systems combine deep learning's pattern recognition with symbolic reasoning's interpretability. Evolutionary algorithms generate and test hypotheses through mutation and selection over generations. These three modern approaches converge into integrated systems that leverage the strengths of each method. Modern systems combine neural, symbolic, and evolutionary components through weighted integration functions. Let's work through a complete numerical example step by step. Imagine we're identifying the type of network intrusion from observed traffic patterns. We observe high packet rate, targeting port 80, with encryption detected in traffic. These three pieces of evidence form our observation set that we need to explain. Hypothesis 1 is a distributed denial of service attack. Prior probability of DDoS is 0.4 based on historical frequency. Likelihoods are high packet rate very likely at 0.95, port 80 somewhat likely at 0.7, encryption unlikely at 0.1. Multiplying these gives score of 0.0266 for the DDoS hypothesis. Hypothesis 2 is an SQL injection attack. Prior probability of SQL injection is 0.3. Likelihoods are high packet rate less likely at 0.3, port 80 very likely at 0.9, encryption moderately likely at 0.6. This gives score of 0.0486 for SQL injection. Hypothesis 3 is a man-in-the-middle attack. Prior probability is 0.2 for this less common attack. Likelihoods are packet rate moderate at 0.4, port 80 likely at 0.8, encryption very likely at 0.9. This gives the highest score of 0.0576. The bar lengths represent the scores of each hypothesis, indicating their relative plausibility.